The objective of this video is to provide 3 examples using intrinsic coordinates. The first example is the following problem. A point or a particle slides on a curve that has the following shape. The equation for the curve is y is equal to minus the natural log of the cosine of x. Now the point is located at this location P, and the projection of P into the horizontal is denoted Q, and the equation is described relative to a point that is located at O, as given in this diagram. Now, the horizontal coordinate is x, and this equation is described then in terms of Cartesian coordinates. So the objective, we're going to be using intrinsic coordinates. The objective of this lecture is to express the velocity and acceleration in terms of an intrinsic basis. And this curve that in this case, this curve that this object slides along is going to be denoted as a track. So we'll denote this as a track. And we'll call that track T. So let's write down the objective. The objective is to determine the velocity and acceleration of P as viewed by an observer fixed to the track and expressed in intrinsic coordinates relative to the track. Now, the way we're going to do this is as follows. This is how we do all intrinsic coordinate problems, and it's the paradigm that arises when you're trying to actually describe things in terms of these basis vectors that such that they lie along these directions, which we've defined as the tangent, the normal, and the binormal. Here's how we do it. We do the kinematics, or we start the kinematics process the same way we would start it with any problem. But then, once we get to velocity, we start transforming everything into intrinsic coordinates. So how are we going to do that in this problem? So in this problem, we start in the standard kinematics format that has been used to solve other problems, which is that we identify reference frames and coordinate systems based on rotations and translations. Now in this problem, there are no rotations. So there's no rotation. So that implies that we need one reference frame. And that reference frame is our base reference frame, which is the track. And we're going to be taking all of our rates of change relative to the track. The coordinate system that is going to be fixed in the track is going to be this one. We're going to put the origin at O. We're going to put EX along OQ. And then EZ is going to be out of the page. And then EY is equal to EZ crossed with EX. Given this coordinate system, the position of point P relative to O will be parameterized as x, EX, plus y ey, which is equal to x ex minus the natural log of the cosine of x times ey. So the first step is the same step that we would take in any kinematics problem, is that we have to compute the velocity of the point in question as viewed by an observer in the reference frame that we're interested in obtaining that rate of change. In this case, we're interested in obtaining the rate of change in the track, so we're going to compute the velocity of point P as viewed by an observer fixed to the track. That is equal to the rate of change in the track of the position of P relative to O. Now, the position of P relative to O is already expressed in coordinates that are fixed in the track, so there's no transport required, so we don't have to apply the transport theorem. And we get the following result by just differentiating the components. The first component, when we take its rate of change, is x dot ex. Now we have to take the rate of change of minus the natural log of cosine of x. Well, the derivative of the natural log is 1 over the argument, which gives us 1 over cosine, so there's a cosine in the denominator. And then the derivative of the cosine is minus the sine, so we get a sine of x in the numerator, but there's a negative sign, and there's already a negative sign, so we get 2 negative signs, so we get a positive, and then we take dx dt. So that completes the chain rule, which gives us that the velocity of point P, as viewed by an observer fixed to the track, is equal to x dot ex plus x dot times the tangent of x ey, which is equal to x dot times ex plus the tangent of x times ey. So that's our expression for the velocity of point P. Now, once we have this velocity, now we start writing everything in terms of intrinsic coordinates. So the first thing we need to do is we know that the tangent vector relative to the track is equal to the velocity of point P divided by the magnitude of the velocity of point P as viewed by an observer fixed to the track, which is equal to the velocity of P divided by the speed. Again, all relative to the track. Now the speed is equal to the magnitude of the velocity. So let's figure out what the magnitude is of the velocity that we just computed. Let's look at this expression. We have the velocity is x dot times ex plus tangent of x ey. Assume that x dot is positive because we don't want to have x dot changing sign. We don't want to keep having this tangent vector flipping by 180 degrees or pi. We just we assume we're going in one direction, and that one direction has x dot being positive. If we do that, then the speed is going to equal x dot times the magnitude of the vector that's in parentheses. The magnitude of the vector that's in parentheses is 1 plus tangent squared x, and then the square root, so 1/2 of that. So this equals x dot times 1 plus tangent squared x is secant squared x, so we get secant squared x raised to the 1/2, which gives us that the speed is equal to x dot times the secant of x. And that gives us a starting point now for being able to express quantities in terms of the intrinsic basis relative to the track. So the velocity of point P is then equal to the speed relative to the track times the tangent vector, which is the tangent vector I just computed. And that is equal to x dot times the secant of x times e sub t. So we've just completed the first part of this, which is we've expressed the velocity as viewed by an observer fixed to the track of that point P in terms of an intrinsic basis relative to the track. Now we have to compute the acceleration. So next, the acceleration of point P as viewed by an observer fixed to the track is equal to the rate of change in the track of the velocity of point P as viewed by an observer fixed to the track. But that is equal to the rate of change in the track of the speed relative to the track times the tangent vector. So this gives us that the acceleration of p is equal to the rate of change of the speed times the tangent vector plus the speed times the rate of change of the tangent vector. So you can see that we have the speed, so we can compute its rate of change anytime we want. I don't have to do that right now. The main thing that needs to be computed now is the rate of change of the tangent vector as viewed by an observer fixed to the track. So the rate of change of the tangent vector as viewed by an observer fixed to the track is equal to, well, let's look at the tangent vector. So the tangent vector is equal to, well, what is the tangent vector? Well, it's the velocity divided by its magnitude. So what we have to do here is we have to write down the tangent vector first. So let's write that down. So the tangent vector is going to equal the velocity, and the velocity, if I've got, it's x dot times ex plus the tangent of x times ey, all divided by the speed, which is x dot times the secant of x. But that is equal to, the secant is 1 over the cosine, so this is equal to the cosine of x times ex plus the tangent of x times ey, which gives that the tangent vector is equal to cosine of x times ex plus the sine of x times ey. Now you can see that the tangent vector is expressed in terms of the basis ex, ey, ez, which is fixed to the track. So therefore, the rate of change of the tangent vector relative to the track, if I'm going to compute this rate of change, the basis vectors are fixed in the track. So this just gives me minus x dot times the sine of x times ex plus x dot times the cosine of x times e sub y. Now if you notice, I didn't have to apply the transport theorem because there's no rotation. Remember, we said that right at the beginning, there's no rotation. So this simplifies to x dot times minus the sine of x times ex plus the cosine of x times ey. Now, recall that the principal unit normal is equal to the rate of change of the tangent vector in whatever frame we're interested in computing the rate of change, which in this case is the reference frame of the track, divided by the magnitude of the rate of change of the tangent vector. So the first thing we need to compute here is we need to compute the magnitude of the rate of change of the tangent vector. So the magnitude of det, dt, and t is equal to, well, let's look at this. Well, if we look at the rate of change of the tangent vector in the track, we see that there's an x dot out front, which I said we're just going to assume that it's going to be positive. So it's going to be, so that the magnitude of this rate of change of the tangent vector is going to be x dot times the magnitude of the vector that's in the parentheses. Magnitude of the vector that's in the parentheses is 1 because we've got a sine and a cosine. So the sum of the squares is sine squared x plus cosine squared x, which gives you 1. So this just simply becomes x dot. And then what we get is that the normal vector, or the principal unit normal, is equal to x dot times minus the sine of x, ex, plus the cosine of x, ey, all divided by x dot, which gives us that en is equal to minus the sine of x, ex, plus the cosine of x times ey. Now, how do we know, well, at least how can we verify partially that we've computed the tangent vector and the normal vector correctly? So one thing we know is that because these are basis vectors, that we know that et dotted with en must be 0. So what happens if we compute ET dotted with EN in this particular case? Well, ET, what's ET equal to? It's cosine x EX plus sine x EY. So we get cosine of x EX plus the sine of x EY, and we take its scalar product with minus the sine of x EX plus the cosine of x EY. And what happens when we take that scalar product? We've got cosine times negative sine plus sine times cosine, which cancels out, which gives us 0. So we've just checked that those two vectors are in fact orthogonal to one another. Now that we've done that, we can write, and we verified this, the rate of change of the tangent vector as viewed by an observer fixed to the track is equal to the magnitude of its rate of change times the principal unit normal. Well, we just said that the magnitude is equal to x dot, so we've got x dot times En. Now we can substitute that result into the expression for the acceleration. And we get that the acceleration of point P as viewed by an observer fixed to the track is equal to the rate of change of the speed relative to the track times the tangent vector plus the speed times x dot times En. And now we can substitute all of the expressions that we had from before, especially the expression for the speed, because that's what we need in here. And we get d dt of x dot times the secant of x times et plus, now what do we get? We get x dot secant of x, that's the speed, times x dot times En, from which we obtain that the acceleration of point P in the track is equal to, well, if we just compute out all the rates of change now in full form, we get x double dot times the secant of x plus the derivative of secant is secant tangent, and then there's another x dot, so we get plus x dot squared secant of x tangent of x, and then that whole thing is multiplied by e sub t, and then we get plus x dot squared times the secant of x times e sub n. So our final expression, if we put it all on one line, is equal to x double dot secant of x plus x dot squared secant of x times the tangent of x times e sub t plus x dot squared times the secant of x times e sub n. Now, one thing that is also useful, although we haven't needed it for any calculations up till this point, is that just for completeness, suppose we compute the principal unit binormal. We know that the principal unit binormal is equal to ET crossed with EN. So let's go back and get these expressions for ET and EN, and let's compute the principal unit binormal. We've got cosine of x EX plus the sine of x times EY, and then we take its cross product with minus the sine of x EX plus the cosine of x EY. Well, what do we get when we take that cross product? We get the following result. EX cross EX is 0, EX cross EY is EZ, so we get cosine squared x times EZ, and then EY crossed with EX is minus EZ, but then we've got sine x times negative sine x, so then there's another negative sign, which gives us plus sine squared x times EZ, which is equal to cosine squared x plus the sine squared x times EZ, which is equal to EZ. So the principal unit binormal is equal to EZ. And if you look at the geometry, you see that that actually makes sense because the motion is in a fixed plane, or in a plane, and the plane is not, there's no twist to the plane at all. So as a result of that, since the plane is not changing, then the principal unit binormal is always normal to that plane, and the normal to the plane is out of the page, which is the direction EZ, which is consistent with the geometry. And when we actually draw the picture, if we go back to this curve, so if I draw this curve again, qualitatively, what this looks like is as follows, is that here's the point P, and here's the tangent vector. That direction is the tangent vector. This direction is the principal unit normal, and then ET crossed with EN gives me EB, which is out of the page, which is EZ. So this is a graphical representation of what we just did mathematically. So that takes care of this example, and the main approach is, again, to make sure that you use the normal kinematics approach until you get to velocity, and then from that point, then you start putting everything in terms of an intrinsic basis relative to whatever reference frame you're interested in computing the derivatives, and in this case we were interested in those rates of change relative to the track. So that's how we did the rest of the problem, and then we got the velocity and acceleration in terms of that intrinsic basis. So that does it for this example. The next problem we're going to do is a similar problem, except for the algebra in this problem is a little bit more complicated, and I want just to show something that has a little bit more complexity, just to show that it doesn't always work out that simply, but the process is the same in these problems. So here's the next problem. The next problem is a particle that's sliding on a parabola. Now the parabola has the following equation. It's y is equal to x squared over 2b, where b is a constant. And again, we've got the projection of this point P into the horizontal, which is going to be labeled Q, and then this distance, or this displacement, is x. And we have a point O, and O is the point from which we're measuring all distances, and again, this is a track. And we're going to label that T. And as we did before, the objective is to determine the velocity and acceleration of P as viewed by an observer fixed to the track and expressed in intrinsic coordinates relative to the track. And we're going to go about this in a similar way to the way we did the previous problem. So again, we see here that the expression, the parameterization of the motion is in terms of Cartesian coordinates, and we have no rotation. So there's no rotation, and that implies that we have one reference frame. That reference frame is the track. That's our base reference frame, and because there's nothing rotating and nothing else translating, we just don't have to worry about any of that. We just have one coordinate system. This coordinate system is going to be the following. It's going to be similar to the one that we had in the previous example. Origin's going to be at O. EX is going to be along OQ. EZ is going to be out of the page. And then EY is going to equal EZ crossed with EX. Now in this case, the position of point P relative to O is going to equal x EX plus y EY, where y is equal to x squared over 2b. So that's our expression for the position. And again, we're going to start the same way we always start. We're going to compute the rate of change as viewed by an observer fixed to the track, because that's the frame in which we want the rate of change. And that gives us x dot EX. And then I have to differentiate x squared with respect to time, which gives us 2x times x dot divided by 2b. So the 2's drop out. So we wind up getting x dot times x over b times EY, which is equal to x dot times EX plus x over b times EY. From this, we can now start to use intrinsic coordinates the way we did before. The first thing we need to do is we need to compute the tangent vector. The tangent vector is equal to the velocity divided by its magnitude, where the magnitude is, as has been defined before, is the speed. So Vp is the magnitude of the velocity, p as viewed by an observer fixed to the track. So let's compute the speed. So the speed is equal to, well, again, assume x dot is positive, and then we get x dot times the quantity, the magnitude of the quantity that's in parentheses, which gives us x dot times the quantity 1 plus x squared over b squared to the 1/2. And if we then use that result, we actually get the following, which is that we can rewrite this as x dot times, well, if we put 1 as b squared over b squared, so we can write b squared over b squared plus x squared over b squared to the 1/2, which results in x dot. Now what we can do is we can factor out a b as follows. We got x dot, and then we've got x squared plus b squared, all divided by b squared to the 1/2. So if we take the square root of this, we get x dot over b times x squared plus b squared raised to the 1/2. Now we have that the tangent vector is going to equal the velocity divided by the speed. So Vpt divided by the speed, which is equal to, let's go back over here, we've got x dot times Ex plus x over b Ey, all divided by x dot over b times x squared plus b squared to the 1/2, which results in the tangent vector being equal to b times Ex plus x over b Ey, all divided by x squared plus b squared to the 1/2, which is equal to Bex plus x Ey, all divided by x squared plus b squared to the 1/2. Now, the next thing we need to do is we need to start computing the rate of change of this tangent vector, because the next thing we're going to need to do is compute the acceleration, and that's going to require us to compute this rate of change of the tangent vector. So the acceleration is, and actually, before we do that, we can do one other thing, which is that if we look here, we can actually look at the velocity now, and because we have the speed is equal to is x dot over b times x squared plus b squared to the 1/2. So we get the speed times the tangent vector, right? Where I recall that that's equal to the speed times the tangent vector. So that's the velocity. Now, let's suppose that we want to compute the rate of change to get the acceleration. So the acceleration is going to equal the rate of change in the track of the velocity of point P as viewed by an observer fixed to the track, which is equal to the rate of change in the track of the speed relative to the track times the tangent vector. This is equal to the rate of change of the speed times the tangent vector plus the speed times the rate of change of the tangent vector relative to the track. So you can see that, as I said, we need the rate of change of the tangent vector relative to the track. So that is going to be our next step. So let's go back over here, and we have this nice expression. So the tangent vector, I'm going to rewrite it actually because it's a little better to rewrite this in a different form. It's equal to b ex plus x ey all divided by x squared plus b squared to the 1/2. But that's equal to x squared plus b squared to the minus 1/2 times bex plus x ey. Now, if you look at this expression, if I'm going to take the rate of change of this, again I'm going to get a product. I have this quantity x squared plus b squared to the minus 1/2 out front, and then I have this vector bex plus xey, and I'm going to have to do the product rule of the first with the second. So I'm going to have the derivative of the first times the second plus the first times the derivative of the second, which is going to result in having to take rates of change of x squared plus b squared to the minus 1/2. So in order to make this a little bit more tractable so that we don't get hung up in too many square roots and powers of 3/2, here's what we're going to do. It's going to make this a little bit easier to keep track of. So I'm going to say let f of x equal x squared plus b squared to the minus 1/2. Now, given the fact that x squared plus b squared to the minus 1/2 is f of x, we know that df dx, which we'll define as f prime of x, is going to equal minus 1/2 times x squared plus b squared to the minus 3/2 times 2x, which is equal to minus x times x squared plus b squared to the minus 3/2. That's a 3. Which is equal to minus x times f cubed of x, because the original function f of x is defined as x squared plus b squared to the minus 1/2, so I just cubed it. Now I'm going to need this result in order to be able to compute the rate of change of the tangent vector. So how does this work? So the tangent vector is equal to f of x times bex plus xey. I just substituted. You see that there's x squared plus b squared to the minus 1/2, and I defined that to be f of x. Now, if I compute the rate of change of the tangent vector in the track, or as viewed by an observer fixed to the track, what do I get? I get the derivative of the first, which is f prime of x times x dot times bex plus xey. And then the second term is plus f of x times the rate of change of what's in the parentheses. Well, the rate of change of what's in the parentheses is x dot ey. But we already know that f prime of x, the way I defined it, is minus x times f cubed of x. So this is equal to minus x times f cubed of x times x dot times bex plus xey, and then plus x dot times f of x times ey, which, if I simplify further, you see that there's an x dot and an f of x common to both of these terms. And as a result, I can factor out the x dot times f of x. And I'm left with the following. I'm left with minus x times f squared of x times bex plus xey. And then I've already factored out the x dot and the f of x. And so I've got plus e sub y. Now, what I'm going to do is I'm going to use the expression for f of x to be able to simplify this further. So here's how we do this. We get x dot times f of x, and then if I distribute the minus x times f squared of x through, I get minus b times x times f squared of x times ex. And then I've got minus x squared times f squared of x times ey plus ey. Now I'm going to actually substitute in for f to make this expression come down to something that is more tractable. I got minus b times x times f squared of x times ex. And then I've got plus 1 minus x squared times f squared of x. The whole thing multiplied by ey. Now, what I need to simplify here actually is this 1 minus x squared times f squared of x. So 1 minus x squared times f squared of x is actually equal to 1 minus x squared. And then recall what the expression was for f. F was this function right here, x squared plus b squared to the minus 1/2. So that's x squared plus b squared to the minus 1. But that is then equal to 1 minus x squared all divided by x squared plus b squared, which, if I rewrite this, I get 1 minus x squared times f squared of x is equal to, now 1 is equal to x squared plus b squared divided by x squared plus b squared. So this gives me x squared plus b squared all divided by x squared plus b squared minus x squared all divided by x squared plus b squared, which gives me b squared all divided by x squared plus b squared. So now, if you look at this expression, I can substitute that expression in, because 1 minus x squared times f squared of x, given the fact that x squared plus b squared is in the denominator, this is now equal to b squared times x squared plus b squared to the minus 1, which is equal to b squared times f squared of x. So now I can use that result in this rate of change of the tangent vector. So I get det dt in t is equal to. So now let's look at this. I've got x dot times f of x, and then I have this expression that's left. I've got minus bx times f squared of x times e sub x, and then I've got 1 minus x squared times f squared of x times ey, but that's equal to b squared times f squared of x times e sub y, which I can then factor out the b and the f squared, and I get b times x dot times f cubed of x. And then if I factored that out, what am I left with? I'm left with minus x ex plus b times e sub y. That is the rate of change of the tangent vector as viewed by an observer fixed to the track. So now we know the following. So we know that the principal unit normal is equal to the rate of change of the tangent vector as viewed by an observer fixed to the track divided by the magnitude of the rate of change of the tangent vector as viewed by an observer fixed to the track. So what is the magnitude of the rate of change of the tangent vector as viewed by an observer fixed to the track? Well, that's equal to, if I assume x dot is positive, I got b times x dot times f cubed of x. And then I have the quantity, that's the magnitude of the quantity that's in parentheses, which is x squared plus b squared to the 1/2. Now that gets divided out to be able to give me the principal unit normal. So the principal unit normal is then equal to b times x dot times f cubed of x times minus xex plus bey, all divided by this magnitude, which is b times x dot times f cubed of x times x squared plus b squared to the 1/2, which gives you that En is equal to minus x ex plus b ey, all divided by x squared plus b squared to the 1/2. And if you go back and look now at the tangent vector, you'll see that the tangent vector is, if I look at the expression, look at back what f of x is. It's x squared plus b squared to the minus 1/2. So what I wind up with is, I wind up with the tangent vector, and I can recall the tangent vector. So recall that E sub t is equal to, let's grab E sub t. E sub t is bex plus xey, bex plus xey, all divided by x squared plus b squared to the 1/2. And just as an aside, and you can check this yourself, which is that et dotted with en is equal to, well, what have I got? Minus x times b plus b times x, all divided by x squared plus b squared, which is equal to 0. So these two vectors are indeed orthogonal to one another, and those are the two vectors. And now what I can write is that the rate of change of the tangent vector as viewed by an observer fixed to the track is equal to its magnitude, which is b times x dot times f cubed of x, and then times x squared plus b squared to the 1/2, times the principal unit normal, which then implies that the acceleration of point P as viewed by an observer fixed to the track is equal to the rate of change of the speed times the tangent vector plus the speed times the rate of change of the tangent vector relative to the track, which is equal to d dt. And now let's go back and get the speed. The speed is x dot over b times x squared plus b squared to the 1/2 times the tangent vector plus x dot over b times x squared plus b squared to the 1/2 times the rate of change of the tangent vector, which gives me another b, another x dot, and it gives me this f cubed of x, which I'm going to simplify all this in just a minute, times x squared plus b squared to the 1/2 times e sub n. But if you recall that the function f was x squared plus b squared to the minus 1/2, right? So if I substitute in that value for the function, I get d dt of x dot over b, and then I've got times x squared plus b squared to the 1/2, which gives me, so I get x squared plus b squared to the 1/2 times et, and then a lot of this winds up simplifying because I get plus, I've got, and the b drops out, I've got an x dot squared, I've got x dot squared times x squared plus b squared, and then times f cubed of x times en. Now, if I simplify that even further, I get that the acceleration of point P as viewed by an observer fixed to the track is equal to d dt of x dot over b. Now, you'll see that there's an x squared plus b squared to the 1/2, which puts an f squared in the denominator because I defined f squared to have a negative 1/2. So this gives me x dot over b times f squared of x times et. And then, if you look here, I've got f cubed of x times x squared plus b squared. So x squared plus b squared is f squared in the denominator. So then I get plus x dot squared, all divided by, I've got an f squared in the denominator. Actually, there's no division, it's just multiplication. I get x dot squared times, and you'll see here that I've got f cubed, and then x squared plus b squared is an f to the minus 2, so I just get times f of x times e sub n, where f of x was, as we wrote earlier, x squared plus b squared to the minus 1/2. So that is the final expression for the acceleration in terms of that function x squared plus b squared to the minus 1/2. And you can see that again, we've decomposed it in terms of an intrinsic basis. Now, this problem does have some algebra associated with it, and the algebra is not obvious, but that's why I actually guided through the algebra in a way that made it a little bit easier to do, but certainly not something that would be easy to do in a time-limited situation. You really have to think through the process carefully and make sure that you keep track of everything very appropriately. Otherwise, you can easily make a mistake. So it's it's fairly complicated. But nevertheless, the process is the same as what it was in the first example, where we write the velocity as the speed times the tangent vector, and then we take the rate of change, and then we need to compute the rate of change of the tangent vector in whatever reference frame we're interested in getting the derivatives, and then we write the acceleration in terms of the tangent vector and the normal vector. And as we did in the previous example, let's just look at one other thing, which is the binormal is equal to the tangent vector crossed with the principal unit normal. And the tangent vector, if you remember correctly, the tangent vector was bex plus xey, all divided by x squared plus b squared to the 1/2, crossed with this principal unit normal, which is minus xex plus bey, all divided by x squared plus b squared to the 1/2, which is equal to, Now, if we take cross products, the denominator is going to be x squared plus b squared. And the numerator, ex crossed ex is 0, ex crossed with ey is ez. So I get b squared times ez, and then ey crossed with ex is negative ez, plus x squared times ez, which is equal to x squared plus b squared, all divided by x squared plus b squared times ez, which is equal to ez. And again, like we had in the previous problem, now let's draw the parabola, and we'll show what that configuration actually looks like. So there's the parabola. Let's see if I can draw this a little bit more curved, so let's see it a little more clearly. Here's the point P, and there's the direction of the tangent vector. There's the direction of the principal unit normal. And then ET crossed with EN gives me EB, which is out of the page. And it's the same type of situation that we had in the first problem. It's just the curve is different, but it's still a two-dimensional. It's a two-dimensional problem. So that takes care of that. Now, given these two examples, we're going to do one more example. Now, this last example is a particle that slides on a helix. And the picture here is a little bit more complicated just because the helix is three-dimensional, but let me see if we can draw this first, and then from the drawing we'll actually start to make more drawings, which hopefully will make the picture somewhat clearer. So a helix is essentially a string, if you want to think of it, or a track that is wrapped around a cylinder. So when you take a cylinder and you wrap a string around it at an angle, you get a helix. And this is what a helix looks like. Now, the helical angle that is formed is defined as beta. And I'm going to put all these things in the diagram slowly so that we can actually see what's going on. The center of the circle that forms the cross-section of the cylinder is going to be called O. And then this bead, which is sliding on this helix, is actually located at this point here, which I'm going to call P. The projection of P into the horizontal plane is going to be called Q. And then the radius of this circle is going to be defined as R. The angle that's formed from where the helix starts here at this point A, and that angle from OA to OQ is going to be defined as theta. And then the angle that the helix forms with the horizontal is going to be called beta. So the helical angle is actually beta. So beta is defined as what's called the helical angle. And it is such that when you look down on this picture and you look down on the circular cross-section, here's what you see. You see a helix. You don't see a helix. You see the quantities. There's the point A. There's the point O. There's the point Q. And then this angle that's formed between the vector from OA to the vector from O to Q, or the direction OQ, this is the angle theta. This is what I'll call a top view. It's a view from above. It's the view as if you were looking down this way. I'll just sketch that really quickly, and then take it away so that we don't get distracted by it. Now, the goal of this problem, and it's the same thing we've done before. The objective is to determine the velocity and acceleration of P as viewed by an observer fixed to the track expressed in intrinsic coordinates relative to the track. And once again, for completeness, this is the track, which is the helix, and we're going to denote it as T. So once again, we're going to go about this the same way we did before, except for this time, we don't have Cartesian coordinates. We actually have cylindrical coordinates. So because the position is parameterized using cylindrical coordinates, we now have to use cylindrical coordinates to start this problem. Remember that I said that when you use intrinsic coordinates, you first have to express the position in terms of another coordinate system, which is an extrinsic coordinate system, such as Cartesian, cylindrical, or spherical. In this case, the position is naturally expressed in cylindrical coordinates, so we're going to use cylindrical coordinates to do the parameterization at the beginning, and then we'll go ahead and then we'll transform everything into intrinsic coordinates. So you can see in this problem that there's one rotation. So one rotation, and that one rotation implies that we need two reference frames. Now, the way we're going to do this is as follows, is that the two reference frames, which is the base reference frame, is going to be the track. Is the track. And that's the frame in which we want all of our rates of change. The first rotating reference frame is the plane, so we have to look at this carefully. It's the plane formed by the direction OQ and OA crossed with OQ. So it's the OQ and the OA crossed with OQ plane. Now, we'll get into the details of why that's the correct rotating reference frame in just a minute, but let's start with the base reference frame. So T is equal to the track. The coordinates that I'm going to lay down fixed to the track are going to have its origin at O. I'm going to put EX along OA. I'm going to put EY is going to be along OQ when theta equals pi over 2. And then EZ is going to equal EX crossed with EY. Now, A is fixed to the helix. It's the start of the helix. So along OQ when theta equals pi over 2 is the location where Q is when I've rotated by 90 degrees from OA. And that's how I got this coordinate system. The next coordinate system, let's call this reference frame. Now that we've defined that, we're going to call this the plane, which is going to be formed by OQ and EZ, where EZ is that direction which is formed by OA crossed with OQ. It's the same thing as long as theta is not equal to 0. That's a well-defined plane. Now, if you want to see that plane, I'll show it to you on the side here after we define the coordinate system. The origin is going to be at O. ER is going to be along OQ. EZ is going to be the same thing as what I had for EZ in the coordinate system that was fixed to the track. And then E theta is going to equal EZ crossed with ER. Now here's that plane. So here is the direction OQ. So there's O and then there's Q out here. And then this direction here is EZ. And it also turns out that this direction is, because if we move O over to the other side, we put O here, then suppose that point out here is A. Then if I take OA crossed with OQ, I also get this direction, that is this direction, which is OA crossed with OQ. They're equal to each other. And this is the plane that is the one that I had just defined for this reference frame A. So if we once again move the point O down here, this is the plane that I'm referring to. This is reference frame. And actually, because I used the point A here, let's change this reference frame nomenclature. Let's call it B. So we'll call this reference frame B. Okay, just so that we don't overload notation. Now, we have everything that we need in order to be able to proceed to solve the problem. The position of point P relative to O, if you look at the original diagram, since P is this point up here, it's the position of Q relative to O plus the position of P relative to Q. And now EZ is also equal to little ez. The position of Q relative to O is equal to R times ER, because this direction in this diagram, that direction is ER, and then this direction is EZ. And the position of P relative to Q is equal to Z times EZ, where this distance here is Z. Now, how are we going to figure out what Z is? Let's look at this diagram here. There's Z. It's right there. That's the distance that I need. That displacement is going to be obtained by flattening out this helix onto a plane. So what we're going to do is we're going to draw this picture. And now this picture is what's going to allow us to compute Z. So how to determine Z? Here's how we do it. When we unroll the helix, we wind up with the following picture. Remember, the helix forms a constant angle with the horizontal. So when I draw the helix, I'm drawing the following picture, which is that this angle here is the helical angle, which is beta. Now, if you look at the diagram, you'll see that the arc of the circle, here's the arc of the circle. Let's draw this in red. This arc of the circle, which is right here, is the same as the arc of this circle that I'm drawing over here. Let's draw it. Close as we can. It's the arc of this circle right here. And because the radius of this circle is r, then the arc of this circle is r times theta. So r times theta. Now, because it's r times theta, we can see from this diagram that this distance right here is going to be r times theta. But the height above the base circle is z, where if I unroll this onto a flat plane, this point here is q, and this point up here is p, which is where the bead is. So from this, you can actually see that z is equal to, well, do it in two steps. We can see that the tangent of beta is equal to opposite over adjacent, which is z over r times theta, which gives that z is equal to r theta times the tangent of beta. Now remember that beta is a constant, okay? So it's a constant angle. It's a constant. So now we have enough information to be able to solve the problem, because the position of P relative to O is going to equal R ER plus R theta times the tangent of beta times E Z. And that's by substituting Z into the previous expression. Now we can get the velocity of point P as viewed by an observer fixed to the track. Well, that's equal to the rate of change in the track of the position of P relative to O. But now we see that the basis ER, E theta, EZ is actually fixed in reference frame B, right? Because we define B to be this plane. So this is equal to the rate of change in B, we have to apply the transport theorem, of the position of P relative to O, plus the angular velocity of B in T crossed with the position of P relative to O. Now the angular velocity of B in T crossed with the position of P relative to O is equal to theta dot EZ, but let's do this in steps first. D dt in B of the position of P relative to O, because the basis is fixed in reference frame B and R is constant, we get R times theta dot times the tangent of beta times EZ. The next thing is the angular velocity of B and T is equal to theta dot times EZ, from which we obtain that the angular velocity of B and T crossed with the position of P relative to O is equal to theta dot times EZ crossed with R ER plus R theta times the tangent of beta times EZ, which is equal to R theta dot times E sub theta. EZ crossed with ER is E theta. So therefore, the velocity of point P is viewed by an observer fixed to the track. If I go get all the constituent pieces, I've got R theta dot times tangent of beta EZ, and I've got R theta dot E theta. So I've got R theta dot E theta plus R theta dot times the tangent of beta times EZ, which is equal to R theta dot times E sub theta plus the tangent of beta times EZ. Now we can start expressing everything in terms of an intrinsic basis. So the first thing I need to do is I need to compute the tangent vector. So the tangent vector relative to this track, or relative to this helix, is equal to the velocity of point P divided by its magnitude. Well, what's that equal to? That's equal to the velocity of P divided by the speed, where the speed is equal to the magnitude of the velocity of point P. Well, what is the speed? So let's compute it. Well, if I look at this vector, if I assume theta dot's positive because we're going, say, up the helix, then we get R times theta dot times the magnitude of the vector that's in the parentheses, which is 1 plus the tangent squared of beta to the 1/2. But tangent squared beta is equal to secant squared beta, so I get R theta dot times secant squared beta to the 1/2, which is equal to R theta dot times the secant of beta. So now I can write the tangent vector. So the tangent vector is then equal to, well, if I go back to the velocity, I've got R theta dot times E sub theta plus the tangent of beta times EZ, all divided by the speed, which is R theta dot, times the secant of beta, which gives me that the tangent vector, since secant is 1 over cosine, I get cosine of beta times e sub theta plus the tangent of beta times ez, which is equal to cosine of beta times e sub theta plus the sine of beta times ez. There's the tangent vector. Now I know that the velocity of point P is viewed by an observer fixed to the track, which is equal to the speed relative to the track times the tangent vector, is equal to r theta dot times the secant of beta times the tangent vector. So now what we can do is we can compute the acceleration. So the acceleration of point P, as viewed by an observer fixed to the track, is equal to the rate of change in the track of the velocity of point P as viewed by an observer fixed to the track. But that's equal to the rate of change in the track of the velocity, of the speed times the tangent vector, which is equal to the rate of change of the speed times the tangent vector plus the speed times the rate of change in the track of the tangent vector. But now let's look at the tangent vector. The tangent vector is expressed in coordinates that are fixed in reference frame B. So therefore, we have to apply the transport theorem to obtain the rate of change of the tangent vector in the track. This is equal to the rate of change of the tangent vector in B plus the angular velocity of B in T crossed with the tangent vector. Now that just comes directly from the fact that we've expressed the tangent vector in terms of a coordinate system or a basis that's fixed in reference frame B, and we want the rate of change of the tangent vector relative to the track, so we have to apply the transport theorem. The rate of change of the tangent vector in reference frame B is equal to 0 because beta is constant and the basis vectors are fixed in reference frame B. The angular velocity of B in T crossed with the tangent vector is equal to theta dot Ez crossed with, what have we got here? Cosine beta E theta plus sine beta Ez. Cosine beta E theta plus the sine of beta times Ez. Now, this gives that the angular velocity of B and T crossed with Et is equal to Ez crossed with E theta is minus Er, and Ez crossed with Ez is 0. So what we get is we get minus theta dot times the cosine of beta times Er, which gives that the rate of change of the tangent vector as viewed by an observer fixed to the track is minus theta dot times the cosine of beta times Er. We can now relate this to the principal unit normal. So recall that the principal unit normal is equal to the rate of change of the tangent vector as viewed by an observer fixed to the track divided by its magnitude. But the magnitude of the rate of change of the tangent vector in the track, well, let's see here. Assume theta dot's positive, assume beta is positive because it's the helical angle. This becomes theta dot times the cosine of beta times the vector that's left over. So if we actually write this, we can actually see this. It's theta dot cosine of beta times minus Er. So it's the magnitude is going to be theta dot times the cosine of beta times the magnitude of minus Er, which is just equal to 1. So from this, we obtain that the principal unit normal is actually equal to minus theta dot times the cosine of beta times Er, all divided by theta dot times the cosine of beta, which is equal to minus Er. So now we can substitute everything in to be able to get this final expression in terms of the tangent and the normal. So let's go back over here. We get that the acceleration So this is the acceleration of point P as viewed by an observer fixed to the track is equal to the rate of change of the speed times the tangent vector plus the speed times the rate of change of the tangent vector. But now, the rate of change of the tangent vector is equal to its magnitude times En, and its magnitude is theta dot times the cosine of beta times Er. Oh, sorry. Yeah, it was theta dot times the cosine of beta times En. Sorry. Because we're writing everything in intrinsic coordinates. So then we have that the acceleration of point P is equal to the rate of change of the speed times the tangent vector plus the speed times theta dot times the cosine of beta times E sub n. And all we did to get that was we just substituted in everything along the way. And now we can actually start taking the derivatives completely out. We know that the speed is equal to r theta dot times the secant of beta. So let's actually start looking at this. Vp is equal to r theta dot times the secant of beta, which implies that the rate of change of the speed is equal to r theta double dot times the secant of beta, because beta is constant and r is constant. The next term is the speed times theta dot cosine beta. Well, that's equal to r theta dot times the secant of beta times theta dot times the cosine of beta, and that is equal to r theta dot squared. Well, the secant is 1 over the cosine, so the secant and the cosine cancel each other out, and we're just left with r theta dot squared, which then implies that the acceleration of point P, as viewed by an observer fixed to the track, is equal to r theta double dot times the secant of beta times the tangent vector plus r theta dot squared times the principal unit normal. And that is the final expression for the acceleration of P. Now, one last thing. It's a little harder to visualize this, but let's look at this helix, and we'll see what directions these vectors actually lie. So when we draw the helix, and you see that it, let's see if I can draw the helix. So if we're on the helix, then this direction is the tangent vector to the helix. This direction, which kind of points towards the center of this circle, is the normal vector, and then this direction, which points ET cross with EN that way, that's the principal unit binormal to the helix. And that's the picture for this particular problem. And what you can see here is that you don't get a really complicated expression. You get a pretty simple expression in terms of intrinsic coordinates, and that's because we use the geometry of the problem. Now there's some algebra that goes along with it, but when you finally get down to this computing the quantities, you see that the velocity, when you express it in terms of intrinsic coordinates, it actually winds up being a very simple expression, and then the acceleration also winds up being quite a simple expression. So that's it for this lecture. We've done 3 examples in a fair amount of detail, and hopefully that illuminates what goes on when you actually use intrinsic coordinates. And we'll look at intrinsic coordinates again when we do kinetics of particles, but for right now this tutorial actually provides a fairly comprehensive instruction on the steps that are required in order to be able to express velocity and acceleration of a point in terms of intrinsic coordinates relative to a desired reference frame.